we are going to discuss IR Spectrophotometer Instrumentation, which we call this as double beam spectrophotometer. An IR spectrometer consists of an infrared source, monochromator, sample holder, detector, and recorder. Common detectors include bolometers and pyroelectric detectors, which convert the infrared absorption into electrical signals. A double beam spectrophotometer is a device that measures how light is absorbed by a sample using the two beams of light. It is used in analytical applications to measure absorption and transmission across different wavelengths. A half mirror splits the light source energy into two beams. One beam passes through the reference side and the other passes through the sample side. The samples in spectrometry can be solids, gases, or liquids. When the beam interacts with the different chemical species in the sample, it will provide enough energy to cause the bonds in those molecules to vibrate in a variety of different ways. A detector measures the sample and reference beams simultaneously, and the recorder records the IR spectrum. IR spectroscopy is the study of absorption of IR radiation, which results in vibrational transitions, mainly used in structural elucidation to determine the functional groups and compounds. IR region is present between visible and microwave region in electromagnetic spectrum. IR of electromagnetic spectrum is divided into three regions. One is near IR. The wave number lies between 14,000 and 4,000 centimeter power minus 1, and corresponding wavelength is given by this range. Middle infrared range, the wave number goes from 4,000 to 400 centimeter power minus 1, whereas far infrared, the wave number lies between 410 centimeter power minus 1. Though slightly differing techniques are followed for the different regions, the basic components of an IR spectrometer are the same. The essential components are light source, sample holder, monochromator and optical material, detector and recorder. In a double beam instrument, the beam is split into two parts. One is directed through the sample cell and the other through the reference cell. The two beams are then compared either continuously or alternatively many times a second. Thus, in a double beam instrument, the fluctuations in the source intensity, the detector response and amplifier gain are compensated by observing the ratio signal between sample and reference. And this is the block diagram of a double beam IR spectrophotometer is shown in the figure. Here S stands for the IR source, which generates IR radiation, and this beam is split into two beams, and both beams, this beam falls on M1 and this beam falls on M2. After getting the reflections from the mirrors, and this beam goes through the reference cell, whereas this beam goes through the sample cell, and this beam falls on the mirror, and this beam also falls on mirror, and they are incident on the beam chopper. And beam chopper usually will consist of a motor. This motor will chop any one of the beams. That is, the motor will continuously rotate. It will go up and down. So when it goes up, the reference cell, the beam from the reference cell will be blocked, and whereas sample cell will fall on the mirror and it will go to the chopper. Whereas if the motor comes down, and the beam from the reference cell will fall on the mirror and it will strike on chopper. So beam chopper will allow any one of the beams, either from reference cell or from the sample cell of the beams, then this beam will pass through the slit S1, and it will fall on the monochromator. Here it is nothing but a grating. So this grating, after the diffraction, and this will pass through S2, and this is a selected beam, the selected range of a beam in a particular range. And after that, this will fall on the detector. The detector will observe the beam and it will send it to amplifier. Amplifier, at the end, amplifier will send it to the recorder, and we will have the IR spectrum on the recorder. This is the working procedure. The source will produce the IR radiation, and this will be splitted into two parts. As shown in the figure, the four optics consist of the source, S, mirrors M1 and M2, and the rotating mirror and the chopper. M1 and M2 divide the source radiation into two equivalent beams, out of which one passes through the sample and the other passes through an equivalent path, which is called the reference beam. The reference holder cell generally contains KBr, potassium bromide, because it is transparent throughout the IR range 4000 to 400 cm/-1. When the beam interacts with different chemical species in the sample, it will provide enough energy to cause the bonds in those molecules to vibrate in a variety of different ways. Thus, the two beams from the sample and from the reference reflect with the other two mirrors and meet at the chopper with a motor, which sends the beam from the reference and the sample alternatively. Thus, the rotating mirror alternately allows the sample beam through the sample and reflects the reference beam with a predetermined period to the monochromator slit S1 and falls on the monochromator, that is grating in the figure. This improves the resolution of the beam. This monochromator will convert the radiation into a particular wavelength. Thus, the monochromatic radiation will pass through the slit S2 and reaches the detector. This slit S2 will allow the radiation only in the range of 4000 to 4000 cm/-1. The detector will analyze the intensity of the radiation, and this radiation is amplified and sent to the recorder. Thus, the recorder will give the IR spectra. Consequently, the detector receives the sample beam and reference beam alternatively. Since both the beams have traveled the same path length, compensation for extraneous effects due to the atmosphere, etc. have been taken care of. Ordinary lenses and mirrors are not suitable as glass absorbs IR radiation strongly. Finally, IR spectrum will be visible in the recorder with a percentage of transmittance and the wave number. The amplified signal is used to move an attenuator, which is nothing but a comb, which cuts down the radiation coming out of the reference beam until the energy balance is restored. This is achieved by a motor which drives a comb into the reference beam when an absorbing band is encountered and out of the beam when the band is passed over. The recorder pen is also coupled to this motor so that the comb movement is followed exactly by the pen. Now let us look at in detail about the types of sources, types of detectors, types of monochromator. First, we are going to discuss on the types of light sources. The ideal source is a blackbody radiator. As it is difficult to have a perfect blackbody radiator, a source which will approximate to it is used. The most commonly used sources are the Glauber filament and the Nernst glow. However, the two most commonly used IR sources are: for the near infrared region, the sources are tungsten filament, nichrome wire, rhodium wire, and for mid-infrared region, the Nernst glow and Glauber sources are used. Whereas for far infrared region, the mercury arc lamp and carbon dioxide lasers are applied. IR sources are hot bodies which emit continuously throughout their infrared region. They require thermal insulation. The radiation source must emit IR radiation, which must be intense, steady, and must extend over the desired wavelength. Now, next one is NRSC glower. NRSC glower consists of a rod or hollow tube about 2 cm long and 1 mm diameter, made by sintering a mixture of oxides of cerium, zirconium, thorium, and yttrium. Platinum wires are sealed to the ends and current is passed through the cylinder. NRSC glower is non-conducting at room temperature. In order to bring it to a conducting state, it must be heated externally. It is maintained at a high temperature using the electrical heating and can be opened in air. It is not subjected to oxidation. Now we'll discuss about Glauber source. Glauber is a low resistance rod of silicon carbide, usually about 5 cm in length and 0.5 cm in diameter. It is more useful in longer wavelengths. The electrical contact with the water cooling is needed. It has an advantage of positive coefficient resistance. When heated to temperature between 1300 to 1300 and 1700 degrees C, it strongly emits radiation in IR region. The disadvantage is its lesser intense source than NRSC glower. It is more satisfactory because it is worked at wave number longer than 650 cm/-1. Both NRSC and Glauber source provide excellent and easily controlled sources for the wavelength band frequencies which are used in the required analysis. However, in the far infrared region, both these sources lose their effectiveness. Incandescent lamp. In the far infrared region, an ordinary incandescent lamp is generally used. It is glass enclosed and has a low spectral emissivity. Temperature can be raised to 1100 degrees C, but it gives lesser energy than NRSC and Glauber sources. An incandescent light bulb or lamp is an electric light which produces light with a wire filament heated to a high temperature by an electric current passing through it until it glows. An incandescent light lamp is an electric light which produces light with a wire filament heated to a high temperature by an electric current passing through it until it glows. The hot filament is protected from oxidation with a glass or quartz bulb that is filled with the inert gas. Rhodium wire. Rhodium wire heater sealed in a cylinder is used. Nichrome wire. It is used when the required wavelength range and intensity are not too great. Now the next title is sample handling. IR spectrometry deals with the measurement of IR spectrum. It is used for the characterization of solid, liquid and gas samples. The material contained in the sample must be transparent to the IR radiation. If we use glass or plastic for analyzing the sample, the IR rays will be absorbed by them. Hence, the plates made up of NaCl or KBr are used to analyze the salts. And as we said, the sample can be either solid, liquid or gas. The solid means solid film techniques. So there are two techniques. One is mull technique, then another one is pressed pellet technique. Here in a mull technique, sample is grinded in a mortar and it will become a paste and we can analyze it. Whereas in pressed pellet technique, the sample is mixed with the KBr and pressed like a tablet and used for taking analysis. And for the liquid sample, liquids are usually examined as a thin film sandwiched between two polished salt plates made up of NaCl. Whereas for gas samples, the sampling of gases can be examined by permitting the sample to expand into an evacuated cylindrical cell equipped with IR transparent windows made up of NaCl. Now we'll go for a monochromator. So as we said, we have used monochromator. We can use prism or a grating. Whereas in the figure we have used a grating. It is the most important part of the spectrometer as it splits the polychromatic radiation into its component wavelengths. This is achieved by using prisms or gratings. Gratings give better resolving power than using prisms. The prism or grating is rotatable mechanically to produce the required frequency. The resolution also depends on slit width and quality of mirrors. Rock salt prism is usually used as monochromator in the region between 650 and 4000 cm power minus 1, though the dispersion decreases considerably above 2000 cm power minus 1. However, the prism instruments are favored because of greater range and simplicity. Neither quartz nor glass is sufficient transparent to IR radiation above 3.5 microns. These cannot be used as they absorb satisfactorily in the IR region. Hence, the crystals of certain halogen salts which transmit IR freely are utilized for optical parts. Quartz is employed as a material for prism construction and is used for near infrared region. The great bulk of analytical work in the IR is done by a crystalline NaCl as the prism material. Beyond 20 microns, NaCl absorbs strongly, so this cannot be used. Crystalline KBr and cerium bromide are satisfactory for the far infrared region, that is 15 to 40 microns. Lithium fluoride provides prism material in near infrared region, that is 1 to 5 microns. Grating is a device which consists of a series of parallel straight lines cut into a plane surface. It offers a better resolution at higher frequency than prism. It is made with materials like aluminum which are not attracted by moisture. It is used over considerable wavelength and long lasting. Now we'll go for detectors, IR detectors. The measurement of IR radiation is difficult as a result of low intensity of available sources and the low energy of infrared photon. As a consequence of these properties, the electrical signal from infrared detector is small and its measurement requires a large amplification. The convenient phototubes are generally not applicable in the infrared because the photons in this region lack the energy to cause photoemission of electrons. Thermal detectors, whose responses depend on the heating effect of the radiation, can be applied for detection of infrared wavelengths. With these devices, the radiation is absorbed by a small black body and the resultant increase in temperature is measured. There are two types of detectors. One is the thermal detector, another one is photodetectors. First, we'll discuss about the thermal detectors. When infrared radiation falls on these detectors, they cause heating, which gives rise to some potential difference. This potential difference depends on the amount of radiation which falls on it. Some of the thermal detectors are thermocouple, bolometer, Golay cell, and pyroelectric detectors. We'll look into one by one. First, we'll discuss thermocouples. It is the most commonly used detector in infrared spectrophotometer. Thermocouples are two dissimilar strips of metals joined together at one end kept with a different temperature. Here, two fine wires of metals which have different thermoelectrical properties are welded with blackened gold foil which absorbs the radiations. One welded joint which we call as a cold junction, is kept at constant temperature, and the other welded joint, which is nothing but hot junction, is exposed to radiations. This exposure of hot junction causes a rise in temperature. Thus, as the two junctions are set at different temperatures, it causes the potential difference, which is proportional to the degree of heating of hot junction. That is the amount of radiations falling on the hot junction. A thermocouple is closed in an evacuated steel casing with an IR transmitting window. KBR is used as a window to avoid losses of energy by convection. Now, this is thermopiles. To enhance sensitivity and to give better results, several thermocouples connected in series are used, and it is called as thermopiles. Now, the next detector is nothing but bolometer. A bolometer is based upon the fact that the electrical resistance of a metal changes with the increase in temperature. The constructed metal or semiconductor that exhibits a large change in electrical resistance as a function of temperature. When the radiation falls on the bolometer, its temperature changes, and hence the resistance of the conductor also changes. The degree of changes in resistance is the measure of amount of radiation that falls on the bolometer. Bolometer is made in one arm of the Wheatstone bridge, and a similar strip of metal is used as a balancing arm of the bridge, which is not exposed to infrared radiation. When there is no infrared radiations fall on the bolometer, the bridge remains balanced. As the radiations fall on the bolometer, the bridge becomes unbalanced due to the change in electrical resistance, and thus the electrical current flows through the galvanometer. The response time is just 4 milliseconds. The amount of current flowing through galvanometer is a measure of the intensity of the radiations falling on the detector. Now the next detector is nothing but thermistor. The functions of thermistor are similar to bolometer, but the resistors are made by fusing together with several metallic oxides, which have negative thermal coefficient of electrical resistance. In a bolometer, as the temperature increases, resistance also increases, but in thermistor, the resistance decreases with the temperature, so negative temperature coefficient. The degree of current flow is a measure of amount of radiation fallen on the thermistor. Golay detectors. In Golay detector, xenon is contained in a small cylindrical chamber which has a blackened membrane. One end of the cylinder is sealed with an infrared window. The other end consists of a flexible diaphragm which is silvered on the outside. A light beam is reflected from this silvered surface to the cathode of a vacuum phototube. When infrared radiation enters the cell, the blackened membrane is warmed, which in turn heats the xenon by conduction. The resulting increase in pressure causes distortion of the silvered diaphragm. As a consequence, the fraction of the reflected light beam that strikes the active surface of the phototube is changed. A change in photocurrent results, which can be related to the power of the infrared beam. The next detector is pyroelectric detector. Pyroelectric detector consists of a thin plate of pyroelectric crystals of 0.25 to 12 mm squared in size. The crystal is placed between two electrodes which are connected to an external electric circuit. One of the electrodes should be transparent to IR radiations. When the crystal is exposed to IR radiation, it absorbs the heat, leading to change in its dipole moment. This change causes generation of electrical charges which are attracted towards the electrodes. The accumulation of charge at the electrode creates a potential. Hence, it produces an electric current in the external circuit. The most common pyroelectric is triglycine sulfate and deuterated triglycine sulfate. Photon detectors. The photon detectors are used in the near infrared region. It consists of semiconductors like lead sulfide or lead telluride. When radiation falls on these detectors, they go to the higher levels and produce signals. The next one is photoconductivity cell. It is a type of a photon detector. It consists of a thin layer of lead sulfide or lead telluride supported on glass. It is enclosed into an evacuated glass envelope. When the IR falls on the detector, the conductance of the cell increases. As the conductance increases, more current flows. The amount of current flow is proportional to the IR radiation. And the last detector is nothing but semiconductor detectors. Semiconductor detectors are one type of photon detectors. They are like insulators when no radiation falls on the detector, but they become conductors when the radiation falls. When exposed to radiation, it causes a very rapid change in electrical resistance, and it shows a rapid response on exposure to the infrared radiation. IR photon displaces the electron in the detector and changes its conductivity. Example, lead sulfide, lead telluride, indium antimonide, germanium doped with copper or mercury. Its response time is less than 1 microsecond, and it is sensitive, rapid, and wide acceptance.